Hello everyone, in this video I will discuss about pericyclic reaction. Okay, and previous video I already discussed that building on, arriving at, and last is looking forward. Okay, so this one I already discussed. So in this video I will discuss this new topic. This is what? See, a new sort of reaction. So actually pericyclic reaction in this reaction is no intermediates reaction. Okay, no intermediates reaction. And I discuss fully this A to Z, that Claydon box. This one is Claydon box. So this line by line I discuss. Okay, so let's start. See, a sort of reaction. Most organic reactions are ionic. So all of you know this. Most organic reaction are what? Ionic, positive or negative. Then electrons move from an electron rich atom towards an electron poor atoms. See, this one is anions or cations are intermediates. So here intermediates will form. The anions or cations are intermediates. Formation of a cyclic ester lactone is an example. Okay, this is example. This one is lactone. Okay, so see, this one is organic reaction, positive or negative. Okay, so this one reacts with this H plus. Okay, then to form this one OH. After that here lone pair is there. This lone pair attack to this carbonyl carbon. Okay, so this pi electron will move from here. Okay, so like this will form, then this one. So after that here this balance, oxygen balance is more than 2 now, so that's why this hydrogen again will eliminate from here. So you will get this one, and this one is water. Again this one is good leaving group, so this one will remove, then you will get this part. Okay, like this. So this is a tautomerization. Now this one like this will form. This is lactone. Okay, lactone. So this one is what? This is organic. Okay, the reaction involves 5 steps. So here how many steps? See, 1 2 3 4. Okay, 5. The reaction involves 5 steps and 4 intermediates. The reaction is acid catalyzed and each intermediate is a cation. So each intermediate, this one is intermediate part, cation part, intermediate, this one also cation, this one also cation, this one also cation. Okay, so here each intermediate is a cation. Electrons flow in one direction in each step. So electrons flow in one direction in each step. Okay, electron flow like this. Understood? Step towards the positive charge. This is an ionic reaction. So this is ionic reaction. In ionic reaction, this intermediates will form maybe cation or anions. Okay, but in pericyclic reaction, no intermediates. Okay, so see, this chapter is about a totally different reaction type. In this chapter is a totally different reaction type. Electrons move round a cycle. Okay, this is circle, sorry. Electrons move round a circle and there are no positive or negative charges on any intermediates. Indeed, there are no intermediates at all. This type of reaction is called pericyclic reaction. So this is pericyclic reaction, means electron move round a one circle system. Okay, the circle system, suppose this one. Okay, circle system, and there are this no positive or negative charge. Okay, no positive or negative charges on any intermediates. This like this intermediate form not there. Okay, not there. Understood? So indeed there are no intermediates at all, this type of reaction is called pericyclic. Okay, this one is pericyclic. The most famous example is the Diels-Alder reaction. Okay, so Diels-Alder reaction, most famous. See this one is Diels-Alder reaction. So you can see here also, this one is what, diene system, and this one another one. So heat will give like this. Okay, this one, understood? This one, this next page you can see, this one also another one. Okay, see, this reaction goes in a single step simply on heating. Okay, simply on heating, this one like this. Okay, this electron, pi electron moves here, this one go here, this one go here. Okay, like this form. So this reaction goes in a single step simply on heating. We can draw the mechanism with the electrons going round a 6-member ring. Okay, 6-member ring, like this electron going round. So this one is 6-member ring. See, 1 2 3 4 5 6, like this 6-member ring will form. Each arrow leads directly to the next, and the least arrow connects to the first. We have drawn the electrons rotating clockwise, but it would make no difference at all if we drew the electron rotating anti-clockwise. That means no difference. If clockwise rotation, then no difference, and if anti-clockwise, then also no difference. Okay, see here, this is clockwise direction, so you will get this part, and if anti-clockwise direction, this one you will get this part. So this one is no difference at all if we drew the electron. So this, see, anti-clockwise, and if anti-clockwise rotation or clockwise rotation products are same. Okay, now see here, both mechanism are equally correct. Okay, this mechanism and this mechanism equally correct. The electrons do not really rotate at all. In reality, the 2 pi bonds disappear and 2 sigma bonds take their place by the electrons moving smoothly out of the pi orbitals into the sigma orbitals. Such a reaction is called a cycloaddition. Okay, so this one is cycloaddition reaction. We must spend some time working out how this could happen. First, just consider the orbital that overlap to form the new bonds. Okay, this is new bonds, this one also new bonds, this one also new bonds. That means, see here, this brown color, okay, this green color also, and this black color also, this one is sigma bond, new sigma bond, here also new sigma bond, and this is new pi bond. So providing this reagent approach in the right way, nothing could be simpler. Okay, so nothing could be simpler. Now see here, the black p orbitals, this one and this one, black p orbitals are perfectly aligned to make a new sigma bond, as are the 2 green orbitals, while the 2 brown orbitals are exactly right for the new pi bond at the back of the ring. Okay, so here new sigma bond, so this one like this, Here also new sigma bond. This one, this black color, this is green color, and also pi bond, this double bond here. Okay, here, as this is a one step reaction, there are no intermediates. So no intermediates, but there is one transition state looking something like this. This is transition state, and this symbol is like this. Okay, this symbol is transition. Okay, this is transition state. So like this, then transition state has 6 delocalized pi electrons. Okay, so you'll get this part. This is stereochemistry also is there. Stereochemistry above the plane. This is called above the plane. This hydrogen above the plane lying. Okay, so now one reason that the Diels-Alder reaction goes so well is that the transition state has 6 delocalized pi electrons. Okay, 6 delocalized pi electrons, thus and thus is aromatic in character, having some of the special stabilization of benzene. You could look at it as a benzene ring having all its pi bonds but missing 2 sigma bonds. So 2 sigma bond missing. 2 sigma bond missing. This simple picture is fine as far as it goes, but it is incomplete. We shall return to a more detailed orbital analysis when we have described the reaction in more detail. Okay, so reaction in more detail, that means that general discussion or general description of the Diels-Alder reaction. This is very important. Diels-Alder reaction general discussion. Okay, so in next video I will discuss that general description of the Diels-Alder reaction, or the Diels-Alder reaction, very important. This Diels-Alder reaction. Okay, see here. Now you have to see next time I will discuss. Okay, Diels-Alder reaction. Okay, and this one is Claydon-Box, very important, and this also this one is standard book for this upcoming CSIR-NET GATE IIT JAM. This one is very important books. Okay, and I will discuss that line by line. Okay, line by line. So please subscribe my channels and share with your friends and likes also. Okay, thank you.